Okay, everyone. So I have told you all about the telescope, and now you can go out and shop for a telescope at B&H or Best Buy and feel really good about it. But the most important part of your purchase is probably the mount that you mount this beautiful telescope on. And so we're going to discuss mounts now because they are very much attuned to the way the Earth rotates. So you can be like me and you can buy an idiot-proof mount, but this way you're going to be even smarter than me and you're going to know a lot more about what you can look for as a beginning astronomer and as an experienced astronomer. So like I say, forget the scope. How do we keep the object in view? It's constantly moving, right? Well, actually, it's not moving, we're moving. The Earth rotates around its axis that goes through the poles. So the stars seem to move around the poles, but of course we're moving. And we need to track that movement in order to take good, clear photographs of Jupiter and the Andromeda Galaxy and everything else we want to see out there. This is called sidereal tracking. And remember, we talked about sidereal in the past in videos as relating to the stars. So we are tracking our celestial body in relation to the stars that are around it. This is a continuous movement of the telescope as the Earth moves to keep it pointed at one celestial object. Now, to do this, let's pretend that we are at the North Pole and you are lying at your back on an ice floe at the North Pole. And the celestial North Pole is at your zenith. I'm using the vocabulary so you get used to astronomical vocabulary. Zenith means right above your eyes, right above your head. That is the celestial North Pole. And your feet happen to be pointing toward Kenya, which is on the equator. All right? And it is 7:40 at night. And when you look up, you see Mars low in the southern sky. And you nod off for a bit. You wake up at 12:40 a.m. Guess what? Mars is very low near the western sky. You wake up in the morning at dawn, and Mars is very low on the northeastern side, sky. So the Earth has rotated during the night, and Mars has seemed to have moved. The altitude of Mars did not change. In other words, it's still very close over the trees, still very close over the trees, still very close over the trees. The altitude did not change. What did change was the bearing. And I want you to look at this again because this should be familiar from one of your labs. Remember, the bearing is the bearing off of looking north and measuring around a 360-degree circle. That means east would be 90 degrees, south would be 180, west would be 270, back up to north at 360. Well, yeah, this bearing did change during the night. And when you were out there at sunset, you were at about 180 degrees from due north. Then at 12:40 around midnight, you were about at 85 degrees off of due north. And then at dawn, you were actually at 355 degrees from due north. You might want to say -5 degrees off of 360. But the way to do it that astronomers recognize is by going clockwise around the circle and saying 355 degrees off of due north. All right. We understand that the Earth's rotation seemed to move Mars counterclockwise. The bearing did change. The altitude did not. So if you have a telescope, you're going to keep that telescope very low to the horizon, and you're going to maintain that angle when you sit up here and maintain a low angle here and a low angle here that you see right here. And then you're going to flip it around and you're going to take the low angle for the northeast side as well. In other words, the altitude did not change, the bearing did. That's known, that bearing is known on the celestial plane of the celestial dome. That bearing is known as an azimuth. And that should be familiar to you from your lab as well. You can review it if you need to. Now, let's go down to the equator. Same night. We flew really fast. And when we're at the equator, we can orient ourselves so we're lying on our back in Kenya. And the celestial equator is at our zenith, right above our eyes. The celestial equator is above us, and the equator is right below us. The ground equator is right below us. And your feet are facing north and pointing north here. And the North Pole is right on the horizon because, again, you're at the equator. So the North Pole is right at the horizon. Same time, right around in Kenya, this is 7:42 our local time. There it's 12:27, which is why I talked to you about those military time changes and Zulu time. All right, so we have got the same time in Kenya, and we see Mars. And Mars now, let's look at the altitude of Mars. The altitude of Mars, it's about 30 degrees higher than the horizon. Horizon's at 0 degrees. It's about 30 degrees up. And that is at our first sighting. And then at right around midnight, which is 1746 local time here, right at around midnight, Mars seems to be about 85 degrees up from the western side, because remember, this would be right at 90 degrees. And when we mark altitudes, we mark them up from the trees, from the horizon. And it's at about 85 degrees up at this point for Mars. And then at dawn time, Mars is right at the horizon again. It's barely over the horizon. So it's got a very low altitude here and a very high altitude here and a pretty low altitude there. But let's look at the bearing. This bearing seemed to go in a straight line right across. And in fact, it did go in a straight line right across the sky for Mars. Up at the North Pole, it showed a real big spin. No big spin here, right across the line. Now, in terms of bearing, we're at about 270 degrees off of due north here. We're at about 90 degrees off of due north here. And we're still at about 90 degrees off of due north here. So here, the altitude definitely does change. And although the bearing changes, it is in a straight line. So let's look and see what we do with our telescope when we're at the equator here. So at the start of the night, you've got a telescope that would be at about 30 degrees off of the horizon. And at midnight, whoa, you've got a telescope that you're pointing at a very high angle. You see that high angle right here. Get my mouse right on there. It's a very high angle. And then by dawn, you've come from that very high angle all the way over, and you're very low to the horizon again and the trees. So although your altitude has changed, you've just effectively gone across in one straight line and gone on one bearing. Let's see, hold on. Let's see what kind of mount is excellent for that. If you happen to live at the North Pole, or if you happen to live at the equator, you're going to love having what's called an alt-azimuth mount. Alt for altitude, azimuth for azimuth or right-left of the bearing. So if you are at the North Pole living with the Eskimos, then you are going to use that right-left function that uses the azimuth around to look for Mars. And if you are at the equator, you are going to use the altitude function and the altitude axis here to go across and take this telescope in this direction. This is not great for time-lapse photography unless you are at the North Pole or the equator. If you are in the middle latitudes, you are going to have to use a combination of the up, down, and the left, right, and we'll get to that in a second. For instance, if you're at Randolph, New Jersey, then you're lying down in Randolph, New Jersey, and the celestial North Pole has now moved into about a little up in the sky. So remember, the equator was right at the horizon. Now the celestial North Pole is about halfway between the equator and the North Star. All right, and at sunset, when you have your feet toward the North Pole and your eyes on the celestial equator that's over you, you'll see Mars at about 25 degrees off of the eastern horizon. And then at midnight, you'll see Mars about 70 degrees up from the southern horizon. And then at dawn, you will see Mars about 15 degrees up from the western horizon. So we do have altitude changes here, 25 degrees, 70 degrees, and 15 degrees. Definitely altitude changes that you would have to accommodate with your telescope. And what's going on with the bearings? Well, with the bearings, you're at about 265 degrees from due north when you start the night. And then at midnight, you're at about 175 degrees from due north. And then by dawn, you're right around 90 degrees from due north. This is not a straight line. And so it's different from the equatorial view that we had. This is a curved line, not like the curve that we saw at the North Pole, but it definitely has a curve to it. So the altitude changed here and the bearing changed to make a curved line as well. When we do that, it doesn't really lend itself to the alt-azimuth mount that we had, because we need to adjust for the altitude and for the azimuth at the same time. We would be doing up, down, and left, right simultaneously. That would lead to a lot of work for us throughout the night, but it would also lead to really poor photography, because that movement back and forth and up and down simultaneously just gets really jerky. Instead, you might look for an equatorial mount. It's great for mid-latitudes, and I hope that this GIF will show you that. If you look at it, it's the telescope axis, and the axis is right here, is mounted parallel to the polar axis that goes through our poles. So that axis is parallel and pointing alongside the axis that goes to the poles. And this axis actually acts as kind of like an azimuth axis going left to right. But this axis actually is parallel to the equatorial plane, or the celestial equator. So that this axis goes parallel to the celestial axis and can keep our Mars in sight all night. Again, Mars in sight all night long by keeping that polar axis in line. This is excellent for time-lapse photography because it takes one of the jerkiness axes out of the play and only one of them moves. Hope that helps you out. You could go with a go-to like I've got, where you just say, find Mars, and it rotates and finds Mars, but then you wouldn't have learned anything. So have a good night. I'll see you on our next video.